Good morning, everybody. Welcome to Organic Chemistry 1, conclusion of Chapter 9. Little opening comment. Test 4 is next Monday, and it looks like we're going to make it out of Chapters 8 and 9, and whatever we get covered in 10 today. But before we can get to that, we have to finish Chapter 9. We have one segment left, and it's called Neighboring Group Participation. And it's a special reaction where two things have to be met, two conditions have to be met before we think of NGP. We need a molecule with a leaving group. We've had that all chapter. Halogen, leaving group, will leave us halide, conjugate base of a strong acid. Now, also in the same molecule, there is an atom with a lone pair. The atom with the lone pair is going to act like a nucleophile, but it's inside the molecule with a leaving group. We have not seen this before. When you recognize that you have a nucleophile, and you're saying, wait, phosphorus is not on my list of nucleophiles, what's he talking about? Well, I want to remind you, nitrogen is on your list of nucleophiles. Phosphorus is underneath nitrogen on the periodic table, so whatever nitrogen does, phosphorus does too. And phosphorus's lone pair is actually a hair more reactive, a teeny bit more reactive than nitrogen because it's not pulling it as close to the nucleus as nitrogen is. So nitrogen a moderate nucleophile, phosphorus moderate plus. How's that? It can be any kind of nucleophile. Anything with a lone pair will cause NGP. And what happens is you do what looks like an SN2 reaction, but it's in the same molecule, so you can't call it SN2. And that will generate a bond that's in a triangle. So this is not a very stable intermediate. After you've generated the triangle, your external nucleophile, the outside nucleophile, will attack, and it'll find one of these two carbons in the triangle. My first example here is got some symmetry. Both of the carbons are identical, they're CH2s, so it does not matter in this example which carbon you attack. You get an oxonium intermediate, which is neutralized by the chloride, or methanol, if that was the solvent, is probably even a better choice here, but I will accept either base, deprotonating the oxonium. You know we do not finish reactions with oxoniums being strong acids. They must be neutralized, and then we're finished. So there's the result. And let's look at another example before we do one of our own. Here we have a secondary carbon with a leaving group, but there's also a nucleophile in the same molecule. This is an override circumstance where all your other analyses would be overridden by this, and you'd just say NGP because there's a nucleophile in my molecule with a leaving group. We'll do a practice example with all the analysis steps shortly. Keeping in mind this is a backside attack on a stereocenter, so when you're finished with the backside attack, an R stereocenter will become an S stereocenter. And now here we have water instead of methanol as our outside nucleophile. Same story though. It has to pick one of the two carbons. Now here's where our knowledge of triangles can be misleading. If that was a halogen in this triangle, then we would have attacked the carbon that spends more time with a plus charge. This reaction is not predicated on stability of carbocations. These triangles are a little more stable than our halogen triangles that we saw back in chapter 6 and 7. So these molecules hang around for a while, and the nucleophile will attack the carbon that's easier to get to. We call it the less hindered carbon. So you have a choice of attacking a carbon that has a methyl and another carbon, two carbon groups, or a carbon that has only one carbon group. That's easier to get to. That's the one that gets attacked. This oxonium, much like the oxonium previously, gets neutralized either by water or the halogen. You could have chloride do the job down here if you want. And you look at this result. In fact, let's look at it here. It's the same result compared to this, and you say, wow, the O didn't even end up on the same carbon as the leaving group carbon. Why? Well, because when we kicked off the leaving group, the triangle had a less hindered carbon down here. That's the one that got attacked. The CH2 ended up with the OH. CH2 with the OH. Stereocenter got flipped in the NGP step. And it's not a substitution reaction, clearly. The O did not end up on the carbon with the halogen. And we got this result. So let's put it to use on a test type question. I stole one from the book here. What we have in our analysis is always carbon with the leaving group. Secondary, we don't know if it's SN1 or 2. We do realize, though, the carbon with the leaving group is in the molecule that has a nucleophile as well. We could add that as like a sentence here, but also has SE new. It's an override. You write NGP. But please never stop your analysis there. Analyze the other nucleophile. ROH. Poor. What does that favor? SN1. And then solvent. When the solvent looks like it's missing, it's the same as the nucleophile. Polar product also favors SN1. But we overrode the SN1 conclusion with NGP. Mechanism, not required, but I'm going to do it. I have trouble myself predicting products from these unless I do the mechanism. So I'd anticipate that many of you would be in the similar situation. I need to see it. So there's my mechanism starting up there. What are we going to get here? We're going to get something that started off as an octagon. Still going to have this octagon around the outside. And what's the back side of a dash? That's a wedge. So there's going to be a wedge bond up to the selenium here. A plus on the selenium. There'd be an H here. Now I have a nucleophile, the alcohol. Why is it going to choose the carbon on the left and not the carbon in the triangle on the right? Why this carbon and not this? This carbon has 2 carbons attached. It has more steric hindrance than the other carbon. We will attack that. And we would generate this here. Watch carefully. A new bond there. New bond to a CH2. That's bonded to a carbon with a selenium. That goes 1, 2, 3, 4, 5. And, oh, there. Correct? Yeah. That's this carbon here. And there's this, the other carbon. And please don't draw that in the box. In the box, you got to lose the H from the oxonium. What would take it? Chloride could take it, or isopropanol could take it. Once again, this wasn't a mechanism question, so really none of this is worth points. But there will be an NGP mechanism worth points in the short answer. So this was not a waste of time. And draw the result. The result looks like this. A bond to a CH2. It's bonded to a ring that's got selenium in one corner. And the ring doesn't have 8 atoms in it anymore. It just has 7. It got smaller. We've had reactions this semester that got bigger rings and some that get smaller. 1, 2, 3, 4, 5, 6, 7. That's a very long bond. There we go. How many CH2s? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. That's the result. So there's some nice review items at the end of this chapter I want you to go over. There's a nice carbocation review with the new information about being allylic added to the list of stabilities of alcohols. There's a nice little flow chart that works for some people, but not for the majority of people who are like me, and flow charts they're just a bunch of pictures. But if you like flowcharts, there's a really nice review about how to follow the logic in this chapter at the end of chapter 9. And that brings to a close chapter 9. And we'll do a brief introduction to chapter 10 before we go to break. Oh, I'm not going to go to page 11. That would be crazy. Here we are. No, that's what we were working on. Here's chapter 10. 3, 2, 1. Okay. My computer's taking a little bit of a break. We'll start with something nice and easy. Nomenclature, alcohols for this course. Highest priority in Chem241. Nomenclature. And later, I already hinted at this. If you have more bonds to oxygen, you get a higher priority. So aldehydes, ketones, carboxylic acids get even higher priority, but we don't get those until the next course. So what does that statement mean about where's carbon number 1? You guessed it. Lowest possible number. And we have 4-methyl. And you can go 1-pentanol if you want. Or you can say 4-methyl, pentan, 1-ol. I know there's new stuff in there, but is it really new? It's very systematic nomenclature. You can even call it isohexyl alcohol. That would be its common name. Name the group attached to the OH. Add the word alcohol at the end. These are all perfectly acceptable names. Okay, not bad. This one, what's more important, the alcohol or the alkene? Well, alcohol. 2, 3, 4, 5. So it's pent. It's got an ene in it. It's also got an alcohol in it. Pent 4-ene 2-ol and a stereocenter. That is definitely R. Won't find a common name for that one. R because 1, 2, 3. Next one, we want the alcohol on the lowest possible number and the alkene on the lowest next possible number. So 1, 3, 4. And looks like we're going 5, 6, 7, 8, 9, 10, 11. Don't forget cyclo. Don't forget 11 carbons. Don't forget there's a double bond between 3 and 4. You don't need to tell me on number 1 there's an alcohol. It's understood. I don't deduct points anymore. If you add 1 OL there, I used to take a quarter point off, and I don't know why. All right, now we got a phenyl group on 1, and this is not a phenyl group on 3. It's a phenyl attached to a CH2. With what we learned in chapter 8, that's a benzyl. 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 So 3 benzyl, 3 benzyl, 1 phenyl. I think I'm going to go 2 lines. And there's a stereocenter and a double bond with geometry in a big ring. And we need to do quick double switch here. If I don't put the numbers down, I often get these wrong. Phenyl's got no H's on that carbon. 4 has to go on the dash. That means it's switched. 4 switched with the 2. And 1 switched with 3. So it's R. And the double bond has Z, E. Oh, that's a good one. Is it Z or E? Let's do it. Near the end of the semester, it's always time for review. Oh, if you haven't figured out now, by now, organic chemistry is always review. We can't move on until we know the new stuff. CH2 phenyl, CH2C with an O. CH2 goes to a C with an O. CH2 goes to a C with no O's. It is Z. There you go. 3 points for that. We're going to do non-N3-ol or 3-nonenol. 2, 4, 6, 8, 9. 3 is the stereo center. If I connect 1, 2, and 3, I get R, and that's what I want. So 4 on a dash. And adjacent gets the wedge. Don't forget, I need a wedge and a dash for stereo centers in nomenclature. And we just reviewed phenol and benzyl alcohol are different animals. Phenol is benzene attached to OH. Benzyl alcohol is benzene attached to C, then the OH. Benzyl alcohol. And I would say allyl alcohol is very similar to benzyl alcohol. Is there a vinyl alcohol? There would be, but it doesn't like being like that. It undergoes tautomerization to be exclusively. This has nothing to do with nomenclature, but this is vinyl alcohol. There's nothing wrong with the nomenclature of it. It doesn't really exist. It's acetaldehyde down here. Wait till chapter 16 for naming those. And then we have a bicycloundecan 1-ol. Move that over here. And I kept the stereo centers off because I don't want to spend too much time on nomenclature. You got your 2 dots. 1, 2, 3, 4. And then 3, 1, 2, 3. And then your 1 looks a little like Texas sideways. 2, 1, 2. And on carbon 1, which is one of the bicyclo positions, you got an OH. And that's that one. So nomenclature will show up on our tests, same amount of points, 14. It's not a big deal, but we can't talk about organic chemistry without it, so it is a big deal. And we're moving on to the good stuff. Yeah, I have a question though. Yes.
I think the no that you drew, it's a S, not a R.
Oh, I better go back and fix that. Let's see. The non-anol I drew is an S, not an R. You are 100% correct, sir. All right. So yeah. To do a quick fix, huh? Watch this. We'll pretend I was never wrong. How about this for a quick fix? So when the number 4 group's on a wedge, you connect 1, 2, and 3, you get S. S is wrong, right? So now it's R. And thank you for catching that, because nothing more frustrating than looking at the notes when there's a mistake in it and saying, I must have missed that part of the lecture. So it's all fixed now. All right. On this page, I've summarized a bunch of reactions. The chemistry's interesting. I just want to point out these are not useful conversions for R OH going to RX. I mean, they're here. You see them. They look fine. So look, I made an R with a bromine on it. Well, in this one, you'd also get pretty substantial amounts of this. Nope, not OH. That would rearrange. You want to see the rearrangement? Here it is. And we haven't seen a rearrangement exactly like this before, but I told you primary carbocations are illegal, so you're not allowed to show them anymore. But what you can do is rearrange and kick off the leaving group, and you'll get this cation here. Never saw the primary cation. So rearrangement. I'm going to leave that. It's supposed to be a rearrangement. I'm out of room. I just want to point out everything on this page has limitations, and we got better reactions coming up on the next page. So put these in your journal, but don't put them as answers on tests for how to make alkyl halides. Okay. So there's good journal entries here. This one's very limited. Only works with tertiary alcohols to make alkyl chlorides. You can't make tertiary alkyl bromides this way. And you're saying, my God, I thought HBr was the same as HCl. Apparently it's not. And I do want to remind you, Br minus is actually a strong nu. So it can do things like SN2 reactions. Cl minus is a moderate to poor nu. Mod/poor nu. So it doesn't like doing SN2 reactions. It can do the SN1 because any nucleophile can do an SN1 on a carbocation. Yeah, limited. So what is the purpose of the first step? The purpose of the first step here is the general purpose of any reaction of alcohols in chapter 10. To make an OH useful, you have to make it into a better leaving group. And one way to make alcohols into better leaving groups is to put a proton on them. Remember, H attached to an acid is called a proton. So protonation is one way to make alcohols better leaving groups. Alcohols themselves are OH minus leaving groups, which is terrible. So just adding a nucleophile to an alcohol doesn't get you anything any day of the week. There's no SN2 reactions with alcohols. There's an SN2 reaction here because it's not an alcohol anymore. Water is an excellent leaving group because it's the conjugate base of hydronium, a strong acid. Okay. So here's one with a branching beta branch. Alpha is the carbon with a leaving group. Beta is one away from that. You can get a HCl to work with this. It'll rearrange the methyl here and right there to a cation, and then it makes a better cation. So I don't think anything's new there. That's all old. We were used to starting over here with a leaving group on here saying can rearrange, make a cation, and secondary cations with a branch one away can rearrange. You get major amount of this because it came from a tertiary carbocation. Tertiary. That's why it happened. Minor amount here. Secondary. And copy those into your journal and then learn these ones much better. We'll spend a lot more time on these. Need to be a little bigger than that. That's tiny. PBr3 is an excellent way to convert an alcohol into an alkyl bromide. And this mechanism looks real complicated. I'll give you the test version of this underneath this, and it's like a 3-point mechanism because there's just so much repetition here. Why does an alcohol attack this phosphorus? That's a good question. Well, phosphorus, with its electronegativity of 2.1, same as hydrogen, is bonded to bromine with an electronegativity of 2.8. That's a polar covalent bond, and there's 3 of them, making phosphorus very positive. So what we have is a backside attack on the phosphorus, and the leaving group leaves. It is a classic SN2 reaction, and you've generated a carbon with an oxonium attached. A carbon with an oxonium itself is an excellent leaving group. So what happens now? Well, first off, it says we do this 2 more times because there's phosphorus is even more positive than it was before. It's got an oxygen instead of a bond to bromine. Oxygen's even more electronegative. So this thing reacts 3 times and you get 3 of these identical groups on phosphorus. And each one of them itself is an excellent leaving group. It's an oxonium. So now you start getting backside attacks of the bromide, which left over here on the carbon with the leaving group. And it happens once and then 2 more times. And you generate 3 of these when you're done. All you're responsible for on the test is this test. Give a mech. Give a mech. And I'll have 2 groups on there already. You don't even need to know what they look like. R2PBr plus, let's do an alcohol. Let's do an interesting alcohol. It's a chiral alcohol. It doesn't look much like an alcohol, does it? And when you're done, you have an H there and a Br here. And the side product looks like this. HO. HO is not red. HO bonded to P, R2. And you don't even need, you don't even need to know what R is. P, R, 2. Please don't change capital R to lowercase r. That would be the element praseodymium, and we never use that in organic chemistry. I still have a student that thinks a boron with 2 R groups is the same as BR2. And this just makes me sad every time I see that. I mean, no. Oh, I got carried away there, didn't I? Okay. So, want a mechanism. So there's our blank version without a mechanism. And this is your favorite mechanism ever because it's going to be so short. Backside attack on the phosphorus. You want to make it look more like a backside attack? Okay, there was nothing wrong with that first one. And it's going to come down here. And you're going to have your blue part. The only thing different in the blue part is it has a new bond. New bond to a P with 2 R groups on it. And the oxygen now has 3 bonds. And you generated an excellent nucleophile. And a backside attack will happen on this stereo center. And that's why you see the flipped stereo center. So this is a nice way to convert alcohols. This would be overall. And PBr3 was the reactant. The end result, the important part, is what happens to the organic molecule. You converted it to a carbon that has a nice leaving group. And the stereo center went from, be careful with stereo centers today, R to S. Why? Because there's a backside attack here. Anytime you do a backside attack on a stereo center, it flips. Put a nice box around it. Segment ran a little long. I will see you after the break. We're going to continue looking at a reaction that puts a chlorine there instead of a bromine. And you'd think, let's just use PCl3. Sadly, doesn't work very well. There's another reagent that works better. We'll see that one real soon, and I'll see you after the break, I think.